Hello friends, we have studied the first chapter sets, relation and function till now. Today we will start the second chapter from algebra, that is divisibility in integers. In this chapter we will learn concept of mathematical induction, well ordering principle, and then divisibility theory in integers. Congruence model and relation, which will prove that it is nothing but equivalence relation defined on set of integers. So firstly, we will study concept of well ordering principle of integers. Well ordering principle. What this well ordering principle states, if you take any non-empty subset of set of natural number, then you can observe that it has least element. Okay, every non-empty subset of set of natural number has least element. Every non-empty subset, yes, of set of natural numbers, set of natural numbers, n has least element, minimum element, minimum element. If you take any non-empty subset of set of natural number, it contains least element. Even though if I take a non-empty subset of whole number set 0, 1, 2, 3, etc., and if I take its subset which is non-empty, then you can observe that it has least element. It is known as the well ordering principle. Then our next concept is first principle of mathematical induction. First principle of mathematical induction. Which was studied in 11th standard also. If you take any statement related with natural number, and if you have to prove that it is true for all natural number, then what we'll do, we'll prove it for 1, we'll assume result for k, and then we'll prove it is true for k plus 1. This concept is known as first principle of mathematical induction. Okay. So let P and B statement related with natural number n. Let P n be statement related with natural number n, related with natural number n such that 1 P1 is true, second for k belongs to n, P of k is true implies P of k plus 1 is true. Then Pn is true for every natural number, for each n belongs to n. This is known as first principle of mathematical induction to the base 1. To base 1. Okay. Other form, let Pn be statement related to natural number or with natural number n, such that 1 Pn naught is true for n naught belongs to n. Second, P of k is true for k greater than or equal n naught, implies P of k plus 1 is true. Then Pn is true for each n greater than or equal n naught. This is also first principle of mathematical induction. If I have to prove some statement which is true for every n greater than or equal n naught, then we'll firstly prove that given statement is true for n equal to n naught. We'll assume the result for k greater than or equal n naught, and with help of the two, P of n naught and P of k, if we are able to prove that P of k plus 1 is also true, then by first principle of mathematical induction, we will say that given statement is true for any natural number. So in 11th standard, with help of arithmetic progression, you have proved that sum of first n natural numbers is, that is 1 plus 2 plus 3 plus dot dot up to n, is nothing but n into n plus 1 by 2. n into n plus 1 by 2. That you have proved with help of arithmetic progression. Here, with help of mathematical induction, we will prove that is true with help of mathematical induction. Okay. So example. So first one, 1 plus 2 plus 3 plus dot dot etc. up to plus n is equal to n into n plus 1 by 2 for any n belongs to set of natural number. For any n belongs to n. So solution. Here Pn statement. What is Pn? Double dot 1 plus 2 plus dot dot up to n is equal to n into n plus 1 by 2. n belongs to n. This is our given statement. Sum of first n natural number. 1 plus 2 is 2 into 1 plus 2 is 3. We'll get here 2 into 3 by 2, that is again 3. If I take 1 plus 2 plus 3, n is 3. 3 into 4, that is 6. Okay. So to prove this one, what we'll do? We'll prove the result for 1. We'll assume result for k and we'll prove it for k plus 1. Okay. Step 1. For n equal to 1, LHS 1, left hand side of 1 is equal to 1. Right hand side of 1 is nothing but, this is my one expression, 1 into 1 plus 1 upon 2, which is nothing but 1 into 2 upon 2, 2 get cancelled, which is 2. Okay. And therefore, LHS is equal to RHS. For n equal to 1, and therefore P1 is true. Now, we'll assume result for any k greater than or equal 1. Okay. step 2. Suppose Pk is true for k greater than equal 1 and k belongs to n. We'll assume that. That is 1 plus 2 plus 3 plus dot dot up to k equal to k into k plus 1 upon 2. To show p of k plus 1 is true. Is true. That is to show 1 plus 2 plus 3 plus k plus 1 is equal to k plus 1 into k plus 1 plus 1 by 2. This is our aim, right? Which is nothing but k plus 1 into k plus 2 by 2. So left hand side of this is say 2, this is 3, okay. LHS 3 equal to 1 plus 2 plus 3 plus k plus 1. I can write this as, I know sum of first k terms is k into k plus 1 by 2. So I will take that terms together. Okay. So this is nothing but by associativity of addition 1 plus 2 plus dot dot up to k and k plus 1 is separate. By second, we will get this to be k into k plus 1 by 2 plus k plus 1. Right? By 2. Then simplifying this, we will get k into k plus 1 plus 2 times k plus 1 by 2, which is equal to, by taking k plus 1 outside, we will get k plus 1 into k plus 2 upon 2, and this is nothing but RHS 3. Right? Thus P of k plus 1 is true. P of k plus 1 is true. P of k plus 1 is true. And then we will say that, therefore by principle of mathematical induction, first principle, therefore by first principle of mathematical induction, Pn is true for any n belongs to n. That is 1 plus 2 plus 3 plus so on up to n. Sum of first n natural numbers is n into n plus 1 upon 2. Okay. What is application of this result? Okay. So note, if I say what is 1 plus 2 plus 3 plus so on up to say 50. Sum of first n 50 terms. This will be 50 into 51, next term by 2, that is 25 into 51. 25 is 1, that is 25 carries 2, 25 fives, 125 plus 5, right? So 130 n into n plus 1. Okay. 25 into 1, 25 carries 2, carry 2. 25 fives are 25 fives, 125 plus 2, that is 127. Is it right? If I take second example, 1 plus 2 plus so on up to 10, I'll get this to be 10 into 11 by 2. 2 fives. 11 fives are 55. So thus if I would find sum of say third 1 plus 2 plus 99 or 1000, 999, I'll get this to be 999 into next term 1000 upon 2, this is 500, and then 2 zeros, 5 nines, 45, carry 4, 9 fives are 45 plus 5, 9 fives, 45 plus 4, that is 49, 4, and that is again 49. 4,99,500. Okay. Sum of first natural number up to 999 is this one. So this result is very important, which we proved with the help of principle of mathematical induction in 11th standard. You have proved it by using arithmetic progression also. Okay, because here if you observe 1 plus 2 plus 3 plus dot to n, it is sum of first n natural number in which first term is a and difference between any two successive terms is 1. So d is also 1. Okay, so for arithmetic progression, for AP here, a is equal to 1 and d is 1. Your Sn is given by n by 2 into 2a plus n minus 1 into d. So n into 2a, 2 plus n minus 1 into 1, again here it will become n 2 plus n minus 1, that is n plus 1 by 2. So by principle of mathematical induction, arithmetic progression result, its answer is just one line. Okay, but for every example, arithmetic progression doesn't work. If you take now next example, sum of squares of first n natural number, 1 square plus 2 square plus dot up to n square, then that terms are not in arithmetic progression or that are not in geometric progression also, and so we cannot apply the result from series. In that case, only arithmetic progression principle of mathematical induction will be useful. So we'll take now next example, sum of first n squares is n into n plus 1 into 2m plus 1 by 6. Second example, 1 square plus 2 square plus 3 square plus dot dot up to n square is equal to n into n plus 1 into 2n plus 1 upon 6. Whatever n belong, natural number n may be. So here Pn, what is the statement related with natural number? That is 1 square plus 2 square plus dot dot up to, keep the habit of writing first three terms of given expression, give three dots, is equal to n into n plus 1 into 2n plus 1 by 6. n belongs to m. This is 1. So step 1, for n equal to 1, left hand side of 1 is equal to 1 square, is 1 square. Right hand side of 1, right hand side of 1 is 1 into 1 plus 1 into 2 into 1 plus 1 upon 6. That is 2 into 3 upon 6, which is nothing but 1, which is here 1. So LHS, from this LHS 1 equal to RHS. From this left hand side is equal to right hand side for n equal to 1, and therefore P1 is true. Step 2, hypothetical step. Suppose Pk is true. Pk is true for k greater than or equal to 1, and k belongs to set of natural number. That is 1 square plus 2 square plus 3 square up to k square is equal to k into k plus 1 into 2k plus 1 by 6. K belongs to n. This k is fixed. To prove P of k plus 1 is true. That is to show one square plus 2 square plus 3 square plus so on up to k square plus k plus 1 square. This we have to show k plus 1, k plus 1 plus 1, k plus 2, and 2k plus 1 plus 1 upon 6. This is nothing but k plus 1. Is it clear? This is your k plus 1 plus 1. If I simplify this is k plus 1, k plus 2, and simplifying this will get this is 2k plus 2 plus 1, that is 2k plus 3 by 6. This is my 2 and this is 3. So left hand side of 3, left hand side of 3 equal to 1 square plus 2 square plus 3 square plus dot dot up to, I will write some of first k terms in one bracket and I will keep remaining terms separately, k plus 1 square. And then by 2, by hypothetical step, P of k is true, I can write this as k plus 1 into 2k plus 1 upon 6 plus k plus 1 bracket square by 2, which is equal to k into k plus 1 into 2k plus 1 plus 6 times k plus 1 its square upon 6. Now I'll take k plus 1 outside. We'll take k plus 1 here outside in bracket k into 2k plus 1 plus 6 times k plus 1 upon 6, which is equal to k plus 1, and then if we simplify this, we'll get this to be 2k into k, that is 2k square plus k plus 6k plus 6 by 6, which is equal to k plus 1 into 2k square plus 7k plus 6 upon 6. Now here if you observe this one, k into 2k, that is 2k square, 3k plus 4k, k into 2k, that is 2k square, k into 3, 3k, and 2k into 2, 4, 3k plus 4k, that is 7k, and 2 into 3, that is 6. Means these two are factors of this quadratic equation. Okay, so this equal to k plus 1 into k plus 2 into 2k plus 3 upon 6, and this is exactly right hand side 3. Thus P of k plus 1 is true. And always write last step. Therefore, by principle of mathematical induction, first principle of mathematical induction of mathematical induction, 1 square plus 2 square plus dot dot up to n square. Sum of squares of first n natural number is equal to n into n plus 1 into 2n plus 1 upon 6. Now for objective questions, if one can ask question, what is 1 square plus 2 square plus, because in present situation you have to face online exams for internal assessment as well as university assessment. So I can prepare a question like this. Note 1 square plus 2 square plus 3 square plus dot dot up to say some 10 square, if I write this. And then 4 options will be given to you. What is it? That is 10 into next term 11 into 20 plus 1, 2 into 10 plus 1 upon 6, which is 10 into 11 into 20 plus 1, that is 21 by 6, then 2 threes, 2 fives, 3 sevens, right? And then 35 into 11. You can do that calculation easily. 55 carries 5 and then 35 11 threes, 33 plus 5, that is Is it clear? If you take say 1 square plus 2 square plus just up to 5 square. Then we'll get 5 into 6 into 5 into 2, 10 plus 1, that is 11 upon 6. This 6 get cancelled, we will get 55. Is it right? So it is not necessary to take what is 1 square, that is 1 plus 4 plus 9 and plus 16 and plus 25. Not necessary to take that one. If you remember these formulas, standard formulae, then for objective questions you can easily give answers, right? So I am giving one exercise. Show that 1 cube plus 2 cube plus 3 cube plus dot dot up to n cube is equal to n into n plus 1 by 2 bracket square for every n belongs to n. So in 11th standard also you have studied the first principle of mathematical induction. We are just revising it, and from point of view of online exam, we have to also try to use these results. Means on your own you have to write few examples and you have to give answer for that. Thanks for listening lecture carefully. Bye bye.